Hi, welcome to another video in database internal series. Today we'll discuss about why binary search trees cannot be used for on-disk based storage for in the context of databases. So this video is actually a part of a 2 video series where I wanted to go in depth about how B trees are leveraged by on-disk based databases. But what I realized was we also need to understand why traditional search trees like binary search tree or 2-3 tree or an AVL tree cannot be used. What are the shortcomings, right? So without any delay, let's get started. So to understand what are the shortcomings, let's first briefly go on to discuss what binary search trees are. So BSTs are sorted in memory data structure and it is used for efficient key value lookup, right? And binary search tree would consist of multiple nodes and each node has a key, a value and 2 child pointers, right? This is what the nodes structure looks like. Okay, so this is just a brief diagrammatic representation of a valid binary search tree. A binary search tree has a root node and there can only be one root node in the tree, and you have then your left subtree and right subtree. Now keep in mind we are discussing all of this in the context of querying a database. Now what happens is each node splits the search space into left and right subtree. Let's assume that you're searching for 3. So what will happen? You are at the root node. You'll see that so before I discuss on that as well, a node key is greater than any key stored in its left subtree and less than any key stored in its right subtree. So this is a property of binary search tree. If you see, 5 is greater than 2 and 5 is lesser than 6. So this is a valid binary subtree. Let's take 2, assume that 2 was a root node. So 2 is greater than 1 and 2 is lesser than 4. So this is also a valid subtree, right? So you will see that for the entire structure of a binary search tree, this property has to be upheld. Then only it is a valid binary search tree. Now let's go back to discuss about in the context of querying, right? Now each node splits the search space into left and right subtrees. What it means is, let's assume that you're querying for 7. So you are at the root node, you see that 7 is greater than 5. So I only need to query in the right subtree. So that is why it is, when I mentioned, right, that it is used for efficient key value lookups, that is why it is efficient. It has already halved the sample space for searching. When you know that you want to search for 7, only look in the right subtree, nothing more to be done. Now let's discuss about tree balancing and why it is important, right? So in the context of databases, right, insert operations, they do not follow any specific pattern, and more often than not you wouldn't be able to make out any pattern to it. So for the sake of brevity and assuming the worst case scenario, let's assume that everything is random. The inserts are always going to be random, and element insertion might lead to a situation where the tree is unbalanced. Now what is a balanced and an unbalanced tree, right? So I'll just briefly go on to the definition, then we'll take a look at the diagrammatic representation. So balanced tree is defined as one which has a height of log base to n. N is the total number of items in a tree, and the difference in height between two subtrees is not greater than 1. So these two conditions have to be satisfied for a tree to be balanced. Okay, now let's go back. So diagram A is a balanced binary tree and diagram B is an unbalanced tree, right? So if you see, both the conditions are being breached in an unbalanced tree. This is also sometimes called as a pathological tree, right? None of these conditions are met, and you'll see that in diagram A, both of the conditions are met which are required for a binary tree to be balanced, right? Now what happens is, an unbalanced tree, isn't it looking like a linked list, right? If you were to search for let's say key 15, you would have to go to node first that okay, I want to search for key 15, this is not equal to 15, then I go to the next pointer, then I go to the next pointer and next pointer and so on and so forth. You will reach the 15th node, right? Now what will happen is your logarithmic time complexity will become big O of n, which is linear, and like, believe it or not, this is not good for databases. We want it to be more efficient. We want it ideally to be log base to n, right, in the case of binary search trees, because that is what this data structure was built for, right? I mentioned in the beginning, it's a key value based data structure, and it is used for efficient querying or lookup, key value based lookups, right? Okay, so without balancing, we have understood that we will definitely lose performance benefits. how the time complexity will become linear instead of logarithmic. Cool. So now let's discuss how to keep a tree balanced. We can do this by something called as rotation around a pivot. So one of the ways to keep a tree balanced is, this is one of the ways to keep a tree balanced, is to perform a rotation step after nodes are added or removed, still considering that addition or removal is random. Now if insert operation leaves one branch unbalanced, I've already explained what a balanced binary subtree is. If any of these two conditions are breached, that means it is unbalanced. So we can rotate nodes around the middle one to make the tree balanced. Now what this means is, it'll get clear with this example. So let's assume you have an unbalanced or pathological binary search tree. What you can do is, you take the middle element as pivot and you just simply rotate the key. What it will do is, it will make the tree balanced, right? This is just a simple approach. Just wanted to kind of brief you about how you can balance a binary search tree. Okay. Moving on to trees for disk-based storage, right? Why binary search tree, is it the right choice, is it not the right choice? Let's discuss on that. So we've already seen unbalanced trees, they have a worst case time complexity of big O of n, right? We have seen that. And balanced trees give us an average of big O of log base 2n, which is way better than big O of n, right? Logarithmic is way better than linear. Now what happens is, due to low fan out, so what is fan out? Fan out is nothing but maximum allowed number of children per node. In a binary search tree, you are only allowed to have 2 children per node. So fan out will be equal to 2, right? So what happens is, due to low fan out, which is 2, we have to perform rebalancing, relocate the nodes and update pointers very frequently. Now this, if you're frequently updating your binary search tree, it is a compute heavy operation, right? And your database performance will get affected by this. If you have to do rebalancing frequently, you have to do rotation frequently, all of this takes time, and of course it will significantly affect your database performance, right? I hope this is making sense. So now let's discuss what are the problems we would face if we were to maintain a binary search tree on a disk based approach to a database. Imagine you are the one who is architecting a database, and you say that, okay, why not, let's use binary search tree and figure out what actually is the problem. Okay, so the problem are actually just two things, and these two things are very significant when it comes to performance. One is locality. So before I go deep into locality, I would recommend you to read about fragmentation. It's a beautiful phenomenon, and how it is solved is also amazing. Maybe I'll cover it in one of the future videos. So do go and read out fragmentation in the context of databases. Okay. So now let's go back to locality. So I've already mentioned, right? We always assume the worst case scenario, that insertion is always going to be random. We cannot control it. There is no guarantee that there is an order to insertion. So there is no guarantee that when that happens, there is no guarantee that created node is written close to its parent. Now node child pointers may span across several disk pages. What are disk pages, I've already covered in one of the previous videos in my database internal series. So if you're curious, do go and check it out. So when your child node is very far away from your parent node, your disk seek has to be done, and it is because it's a disk seek, and these structures, let's assume you have a hard drive and your disk head has to rotate to go to the farther child node. It's again going to deteriorate your database performance. So ideally you would want to keep your child nodes as close to your parents as possible to optimize for performance. You want locality to be as close as possible, right? Understood? Cool. Now the second problem that comes is the tree height. Now since the tree height is log base 2n because of the low fan out, what happens is you have to do that many disk seeks and that many disk transfers, right? What that means is, because your tree height is like higher compared to let's say a B tree, if we were to use that data structure, you have to do that many disk seeks and that many disk transfers, and these are expensive operations which can significantly affect your database performance. Small node sizes make these kinds of data structures like binary search trees, 2-3 trees, or AVL trees impractical for on-disk storage. So now we have understood and we have pondered upon these two problems which make binary search trees impractical. Like, that is the verdict. We like pondered if BST is the right choice, and we have clearly understood that even though the time and logarithm like space complexity is technically considered as optimal, why it is not suitable for on disk. I know it is a little counterintuitive, but when it comes to databases, these nitty-gritties and these details matter, right? Okay, so hope I made sense until now. Now, considering these factors, a version of tree would be better suited for disk which has the following properties. Now we know what exactly the problems are, so we know, okay, this is what we have to solve for. We want to have a high fan out. What is fan out? Fan out is nothing but the maximum allowed number of children per node. Instead of 2, let's say if you were to have 3 children, right, it would be better for us. Why it would be better for us? Because we would want to improve locality, right? Okay, and we also want to have a low height to reduce the number of disk seeks during traversal. Just taking time and space complexity into account for a data structure is not enough when it comes to the context of databases. This is what I wanted to kind of bring forth and tell you that, even if you have a very efficient data structure on paper, it may not be suitable for on disk storage in the context of databases, right? So I hope this made sense and you now understand why binary trees cannot be used for on disk storages. Now you know what the problem is. So in the next video, we'll discuss on how B trees solve these two issues, the issue of low fan out and like larger height, right? So thank you for this one, and I'll see you in the next one.